With this video, we're going to look at what I call population biology. And remember, population is a group of one species in a certain area at a certain given time. And population biology is important to understand so that you can see like natural selection and what's happening in the environment. Because some populations have to worry about competition and running out of food while others don't. And we're able to see a very specific pattern when we look at the data behind population biology. Now, again, like I said, remember, population is a group of organisms that are all the same species in one area. So, for example, we have a population of zebra. And when we look at population growth, we want to see, how are these species surviving in that area? Do they have a boom? Are they having, lots of these creatures die off? And see, an overall pattern as to their growth. So population growth is the change in size of a population over time. So for example, you can see here in this graph, we're looking at humans and we've got years down at the bottom, and then we have the population in the billions. Now in the 1750s, it looks like that there was a little less than 1 billion people in the world. Now how they figured that out, I don't know. But notice by the time we get to 2150, it's estimated that we're going to have a population of over 10 billion people. And you'll see here how this curve has this very interesting shape to it. For, 1750s to about 2000 or to about 1950, it's just like this nice level crease. And all of a sudden there's like this huge spike, and then it starts to level off again. This is a graph that we call an S-shaped curve. And we're going to talk about that later on in this video. Now, populations do not experience linear growth, which is what we see with a straight line, because populations are not steady. There's times where populations have like a huge explosion, a burst, and then there's times where populations, unfortunately, might have this huge amount of people or species dying at a certain time. So when we look at the data for populations where we record, like the census, how many people are living in an area at a certain time, we don't get this nice straight line. And this is what we call linear growth. What we find is that populations show what's called exponential growth, which basically means that the population multiplies every so many years. It's just not like this nice constant pattern that forms this nice straight line. We get this thing that we call like this J-shaped curve. And so populations show exponential growth because the more individuals there are, the more offspring they can produce. So, we might start off with 2 people, they have offspring that's now 4, and then those 4 have offspring, and it's now, goes to 8, those 8 have offspring, it goes to, who knows, 32. And so the numbers keep getting bigger and bigger and bigger and bigger. And so we can have this steady spike that goes up. And this is an example of what we call a J-shaped curve. And when we see a curve like this, when we look at populations, it's going to mean a certain thing. And again, we're going to talk about that later in this video. Well, in the case of what we call the J-shaped curve, so we're now later in this video, this is what we call unrestricted population growth. Basically, this means that the individuals in this population, whatever population we're looking at, they don't have to worry about anything. It's unrestricted. Nothing is determining how many offspring that they can have. They have plenty of food, they have plenty of water, they have plenty of space, they have plenty of mates. So their population growth is unrestricted. Basically, they're not running out of anything. So they can just have as many children as they want and not have to worry about it. Well, that's not the case for all populations. And so when we look at this information, we also have to look at what's called population density. And when something's dense, that it's thick. So basically this is, the thickness of the population. As you can see in this data here, remember the original 13 colonies were on the East Coast. And over time we worked our way over to the West Coast. Well, if you notice, the East Coast and the West Coast are densely populated. The East Coast is probably very densely populated, 1, because it's near the coast, it's near the beach. And 2, these are the original 13 colonies. And on the West Coast, it's probably densely populated because 2, it's on the beach. And people from Asia have migrated across the Pacific Ocean in order to live here. And the area in yellow, which is kind of like, Nevada, Arizona, Wyoming, lots of deserts, lots of harsh mountain regions. There's less people living in those areas. So what does that have to do with this J-shaped curve? Well, populations cannot grow indefinitely, which is what a J-shaped curve is showing. With J-shaped curves, this is unrestricted population growth. Well, eventually, as the population gets more dense, as more and more people, for example, or more zebras start to live in an area, they're going to have to start figuring out, okay, what are we going to do? We're going to start to run out of stuff. And these are what we call limiting factors. When you limit something, you stop something from doing whatever. So limiting factors are things that can stop a population from growing. And with limiting factors, we divide them into two groups. The first one is what we call density dependent. Well, density dependent means it depends on how many people live in that area as to whether or not it's going to be a big deal. So for example, food. Food would be a density dependent limiting factor. If the population is small and there's a lot of food available to them, food is not something they have to worry about. But if the population is very large and they only have a certain amount of food, food is something they have to worry about. So how much food and whether or not they need to worry about it will depend on how big the population is. So density dependent factors, it depends on how big that population is as to whether or not it's going to be a big deal. So for example, if you were like a group of 10 and you landed in a shipwreck on this huge island and there's plenty of fruits, there's plenty of food, you're able to hunt with no problem. Well, that party of 10 is not really going to worry about running out of food. But as they settle down, form families, and the population grows and grows and grows and grows, eventually food can become a problem. So again, density dependent factors, things like disease, competition, food, it's going to depend on how many things are in that population as to whether or not this is going to make a big deal. That's different from density independent factors. With density independent factors, it does not matter how many things live there. And most of these are going to be weather or environmentally related. So for example, a tornado. A tornado is going to form and cause destruction no matter how many creatures live there. Okay? A tornado can happen in a big city such as Raleigh, North Carolina, or a tornado can happen in a Midwestern field with no houses around. The tornado is still going to go through and it's still going to cause destruction. It doesn't depend on who lives there. It doesn't care. Okay? A volcano is going to explode. It doesn't care if there's a village or a huge city nearby. It's going to explode. So density independent factors affect the population the same way regardless of how many creatures live there. Okay? A flood is going to flood. It doesn't matter if it's flooding an empty field or if it's flooding New York City. A flood is going to flood. It's going to cause destruction. And these are examples of what we call density independent factors. And most populations, when they first begin, start with a J-shaped curve. They have plenty of resources. They have plenty of food. But eventually, they get to the point where their populations are so big, they can start running out of things. And that's going to change the shape of our curve. Because eventually, the environment will reach what we call carrying capacity. So basically think of it as capacity is what you have the ability to do. And so how much can you carry? You guys know if you were to stretch your arms out and I were to start to stack books on your arms, eventually it gets to the point where you just can't hold any more books and you're just going to drop all of them. Well, that's your carrying capacity. Well, environments have a carrying capacity. This is how much can I take care of before I start running out of things. So it's the maximum number of organisms of one species that can be supported for an indefinite amount of time. So going back to this example of this island that they shipwrecked, this party of 10 found. As the population gets bigger and bigger and bigger, they're going to find they might start running out of food. They might start running out of land. competition starts to kick in. The environment can only hold so much. There's only so much food in an area. There's only so much water in an area. So carrying capacity is kind of like the ceiling. I can't, I'm done. I cannot take any more. It's the environment's breaking point. So as long as you're below carrying capacity, your population will be fine. Your population will be able to grow, and you don't have to worry about running out of things. As you get close to carrying capacity, the population decides, okay, we need to slow down, we need to conserve things. Because if you go over carrying capacity, the environment is at a breaking point. And if you go over carrying capacity, you will run out of things and things will die. So when the size of a population becomes larger than the carrying capacity, limiting factors will come into place. And so we have to look at death rates versus birth rates. Birth rates obviously are how many of this creature is born in an area at a certain time. And as long as there are no limiting factors, the population can continue to grow. So the birth rate will be very, very, very large. The red line here represents the average of the data. And you can see at about 6.5, it levels off. That is the sign for what we call carrying capacity. That's the ceiling. That is as much as the environment can take. So if you'll notice, the population grows so that it goes over that red line, it then drops. If you go over carrying capacity, there's not enough resources to take care of that population, and things will begin to die off. And so you'll see it drops down below carrying capacity, and then eventually the population regains its strength, it begins to grow again, so it goes up and down, up and down, up and down. But the average there represents your the red line. So when a population has reached carrying capacity, this is what we call restricted population growth, and this is what we call an S-shaped curve. As long as you have a J-shaped curve, okay, the J-shaped curve lets you know that the population is still going strong. And what I mean by that is the population has not yet reached carrying capacity. The environment has not reached its breaking point. There's plenty of food, there's plenty of resources. However, when you do get to that breaking point, which is what we call carrying capacity, and as you can see here, carrying capacity is often abbreviated as the letter K. And if you see a graph, a lot of times you'll see this dotted line. If you see a graph of this dotted line, it is a population growth graph in most cases. This dotted line represents the ceiling. It's the carrying capacity. It's the breaking point for the environment. And so with restricted population growth, you can see here for a little while, we had a J shape. So the population was doing fine. It wasn't running out of resources, but eventually the population got to the environment's carrying capacity and the average levels off. Okay. Again, in the real world, you can go above carrying capacity. If you go above carrying capacity, you'll then drop right back down. So it is possible that a population goes above carrying capacity. If that happens, there'll be high death rates. And so if there's high death rates, it'll drop back down. Well, if it's below carrying capacity, again, it can have high birth rates, but if it crosses carrying capacity, it will have high death rates and it will drop back down. So overall, if you take the average, you get this straight line. And so that leveling off represents carrying capacity, and this is what we call an S-shaped curve. And what we find is most creatures in nature fall into one of two patterns, what we call a life history pattern. We'll find that they either can have a J-shaped curve or they have what we call the S-shaped curve. When we look at life history patterns, you either have a rapid life history pattern or you have a slow life history pattern. Rapid life history patterns, I always remember these creatures do not live very long. So they have to live their life really fast. So they have to do everything really quickly. They have to do everything really rapidly. Slow life patterns, these creatures tend to live a long time. So they don't have to rush through things. But in rapid life patterns like this mosquito here, they are not going to live very long. So they're going to reproduce very, very, very quickly. In something like a mosquito hatches out of the egg, and the female within a matter of days is ready to reproduce. Now that's different from something like humans. It takes 14, 15, 16 years for a human female to be ready to reproduce. So we take things a little bit slower. But with rapid life histories, because they have to live their life really, really, really fast, they reproduce very quickly. They tend to produce a lot of offspring. Okay? One fruit fly can lay hundreds of eggs. Now we know not all of those hundreds of eggs will live, but one fruit fly can lay hundreds of eggs at one time. They tend to be very small. They don't have time to grow big. They mature rapidly. They have to be able to reproduce very quickly. And they don't live very long. Okay? They can live in unpredictable, changeable environments, and the population size fluctuates. Basically, rapid life patterns have J-shaped curves because since they live such short, fast lives, they don't have to worry about running out of anything. So their growth pattern tends to be a J shape. They don't have to worry about running out of things because they're not going to live that long. That's different from a slow life pattern. We tend to be S-shaped curves. Because we do everything slower, we live longer, we do have to worry about running out of things. So since we live longer, we can take things slower, we reproduce slower, we produce few offspring because we have time to take care of our children. We're not like a mosquito that has to lay as many eggs as possible. You know, if you lay 100 eggs, maybe 10 of them will survive. We have time to take care of our children. We have time to grow. We have time to mature. We have longer lifespans. And our population tends to stay near carrying capacity. Now, for the most part, the human population is still in a J-shaped curve. We're still growing exponentially. But if you look at certain areas, we are some areas that are in carrying capacity. And so just remember some interactions between organisms that can limit the size of a population. Predation, okay, predator prey. If you have a lot of rabbits in an area, the coyotes have plenty of food. So if you have a large population of rabbits, the population of coyotes can get large. But if the population of coyotes get large, then the population of rabbits are going to start to drop because the coyotes are eating them. Well, if the population of rabbits drop, then the coyotes are going to start to starve, so that population will drop, which then means the bunnies can start to rebound and the population can get bigger. So they're going to go up, down, up, down, up, down. Well, if you begin to reach carrying capacity, you begin to run out of food, you're also going to have to worry about competition. Okay? You're going to have to fight for what you have. Okay? In unrestricted growth, there's plenty of food to share. You don't have to worry about it. But as you get close to carrying capacity, competition will kick in. And at the same time, crowding. Okay? Again, in unrestricted, you've got plenty of room. You don't have to fight over where you're going to live. But as you reach carrying capacity, crowding and stress does become a problem.